seen the problems here. So in general form, general optimization problem, we have an objective function, f0x. We have linear inequality constraints, fix smaller or equal than 0, as you see here. And we also have hi constraints, which is hi is equal to 0, which are equality constraints. And in this case, by using these optimization problem, our goal is to find an optimal solution that minimizes this f0 while satisfying all the constraints. So that will be our goal in this optimization framework. And in this case, we have different definitions as well. We have feasibility. So for instance, a point in the domain of f0, so domain in the objective function is feasible if it satisfies all the constraints. So in this case, for instance, for f0x, for x, we can give any value we want and we can get some f0 function. However, for the constraints, doesn't guarantee to be satisfied for fi and hi. So in this case, if constraints are not satisfied, then this problem becomes infeasible. However, if the constraints are satisfied, then this problem becomes feasible. And again, a problem is feasible if it at least one feasible point and feasible otherwise. If there's at least one feasible point, a problem is feasible because that feasible point can be a solution. And in this case, the optimal solution is among feasible points. So given x in Rn, for instance, let's assume that x is in Rn, only subset of these Rn, so in n space are real numbers. And in this case, only subset of these x values will be basically feasible, and optimal solution will be among these feasible points. So an optimal solution will be among these feasible points. And a feasible point is basically an optimal if f0x is among the optimal sets. So for instance, it's locally optimal if it's optimal within the ball. So optimal is basically optimal among all optimal points. And if it's a locally optimal point, then it will be within a ball. So in this case, I'm skipping these global and local optimality. This is same as the one that we have seen in the convex set. So in this case, in the standard form of optimization problem, we have explicit constraints. So domain of feasibility is basically domain of the constraints by fi, which are the inequality constraints, and intersection of the constraints hi, which are the equality constraints. So hi, if you remember, was equality constraints. And fi was basically inequality constraints. Inequality constraints. In this case, intersections of these constraints is the domain of the problem. And in this case, basically, if a problem is these are explicit constraints, so for instance, like explicitly, we basically mention these constraints. They cannot be deduced from the problem definition. So a problem is said unconstrained if there's no explicit constraint. So for instance, if a problem is only made up of objective function, then the problem is basically unconstrained. Only objective function. If it's only objective function, then it's basically unconstrained. And however, depending on what's the problem, what's the function in the objective function, the problem, there might be implicit constraints as well. So for instance, in this case, if you want to minimize x, given that logarithm of, minimize the logarithm of b minus a transpose x, then in this case, since logarithm is only defined for the condition it's greater than 0, then B should be greater than A transpose X. And in this case, this constraint, B greater than A transpose X, is an implicit constraint. And again, feasibility problem is, so in even though we are dealing with the objective functions or the optimization, so in some cases, we don't really want to minimize the objective. So in some cases, we just want to find basically a feasible point. For instance, we don't have any objective that we want to minimize, but basically we have constraints. So we have Fix constraints here and Hix equality constraints here, but we don't have any objective function. And in this case, what happens is that we try to find an X, and in this case, we basically just satisfy these constraints. And again, this is just a feasibility problem. This is called a feasibility problem. And feasibility problem is a special case of basically the general problem. So in this case, we can formulate as in the general case where we put the constraints where Fix is smaller or equal than 0 for I equals 1 to m, and Hi from 1 to p is equal to 0. And in this case, basically, we try to basically minimize the 0. And in this case, if we find a solution in this case, then this problem means it's feasible. So if we find any solution, it doesn't need to be optimal here because we don't have any objective function here, then that's called feasible. And if basically we cannot find any solution, then the problem becomes infeasible. And the one subtype of optimization problem that we will deal in this course is convex optimization. And in standard form, convex optimization is something like this. So we have again F0x. It's slightly different than the formulation is slightly different than general optimization problems. So we try to minimize x given F0x, which is the objective function here, objective function. And then we have inequality constraints, which are Fix is smaller or equal than 0, where I is from 1 up to m. And we have this inequality constraints, and we have equality constraints. For equality constraints, that should be linear equality constraints, because all other equality constraints are non-convex. Linear equality constraints because they are convex. So for instance, if we have here a quadratic equality constraint, that is always non-convex. Because in this case, equality means that it satisfies both cases. So Ax should be less than B, and A times X should be greater or equal than B. So equality means both of them are satisfied. And since this should be convex, this is only valid where this is basically an equality constraint. That's why we have only linear equality constraints for equalities. And in this case, in order this function or this optimization problem to be convex, F0, the objective function, as well as the remaining constraints, F1 up to Fm should be convex. And again, since this is convex, the one important property of the convex function is local optimas are global optimas. So any local optimal point will be global optimal point. So that's why in this case, this is quite important. And again, most problems are not convex when formulated. So when we first formulate the problem may not look convex, but it will be actually a convex problem. So again, by formulating problems as convex optimization problems and by knowing which functions are convex, then basically we will easily come up with convex formulation. And again, let's look for an example. Let's assume that we try to basically minimize x1 square plus x2 square. And that's what we want to minimize. And that will be subject to the fact that x1 divided by 1 plus x2 square is smaller than 0. And x1 plus x2 square is 0. So in this case, first of all, this is a non-convex function. So we can tell that it's a non-convex optimization problem because this is not a linear expression. And we have a quadratic expression, quadratic equality expression, which is not convex. Since at least one of the constraints is non-convex, then the problem becomes non-convex. The objective is convex, so there is no problem for this, but we can transform this problem into a convex problem. So the last constraints show us that x1 should be equal to minus x2. And by definition, this should be the case. And in this case, if we have this equality constraint, then we can write the objective function as x1 is equal to minus x2, so which will be linear. And again, we can replace this non-convex x1 divided by 1 plus x2 square smaller than 0 by x1 smaller than 0, because that will always be positive and that won't have a result on the value, and it will turn into x1 is smaller or equal than 0. And again, if we put this x1 is equal to minus x2 in this linear equality, then the problem can be formulated as becomes a convex formula, isn't here. First of all, inequality constraint is x1 is smaller than equal to 0. That's convex. So equality convex is equality constraint x1 plus x2 equal to 0. And that's also a convex constraint. And the objective function, which is x1 square plus x2 square, is also convex. And that's why this problem will be a convex problem. And again, there are equivalent formulations. So for instance, here, let's look at some equivalent formulations. So for instance, assume that we have this AXB condition. So we have this F0x. Again, this is the objective function. We have inequality constraints Fi, and we have equality constraints AX equal to B. And in this case, we can transform this problem without the equality constraints, and we can basically eliminate the equality constraints by defining x as fz times x0. So we basically replace x with fz plus x0 such that AXB is satisfied. So in this case, we basically find f and x0 such that x equals to fz plus x0 for some z is satisfied. And in this case, we replace x with f0 plus x. And then the minimization problem becomes over z instead of x. And it becomes f0's fz plus x0 and fi f0 plus x0. And that's one way to eliminate the basically constraint. And again, another way is basically equivalent formulation is addition of slack variables. So slack variables are variables to turn inequality constraints into equality constraints. So for instance, here we have this f0x, and in this case, ax is smaller than b0, and we can turn this into a linear equality constraint by sing si, which is smaller than 0, and then turning into an equality. So previously it was a times x, ei transpose x, smaller than bi for each vector x. And in this case, what happens is that we add si, and ai transpose x plus si is equal to bi. And in this case, since this was smaller or equality, then si should be greater or equal than 0 in order this condition to be satisfied by using slack variables.